Hi, my name is Mirza, and I'll be presenting the vertex cover at distance on H3 graphs, a joint work with Clement Dallard and Martin Milanic. Let's start with some definitions. A vertex cover in a graph G is a set of vertices intersecting all of its edges. If G is the following graph, then this set of red vertices is a vertex cover because every edge of the graph has at least one endpoint that is a red vertex. If we relax the definition of the vertex cover and for a non-negative integer k, define a distance k vertex cover in a graph G to be a set of vertices such that every edge has an endpoint that is a distance at most k from a vertex in that set. And taking the same graph as before as an example, for k equals to 0, the following set of red vertices is a distance 0 vertex cover because every edge has an endpoint that is a distance at most 0 from a red vertex. An endpoint is a distance 0 from a red vertex means that that endpoint is a red vertex. So the case when k equals to 0, that is the distance 0 vertex cover, corresponds to the vertex cover. When k is equal to 1, this set of red vertices is a distance 1 vertex cover because every edge has an endpoint that is a distance at most 1 from a red vertex. And when k is greater than or equal to 2, this one edge will suffice to cover every this one vertex will suffice to cover every other edge in the graph. That is, for every edge will have an endpoint that is a distance at most k from the red vertex. Now that we have defined the distance k vertex cover, we can define the distance k vertex cover problem, which asks, given a graph G and an integer L, whether G contains a distance k vertex cover of size at most L. An application of the problem lies in the field of network monitoring, where, as usual, we have hosts, and the hosts are connected by links. And the links need to be monitored from hosts. However, a host can monitor only links at a certain distance. And if links can be monitored from hosts a distance at most k, looking for a set of hosts that monitors every link is equivalent to looking for a distance k vertex cover. And since we want as few hosts as possible, we want to minimize the number of hosts needed for the monitoring. That is, we want to minimize the distance k vertex cover. In the case when k equals to 0, we, as said before, have the vertex cover problem. That problem is equivalent to the independent set problem and was shown in 1972 by Karp to be NP-complete. When k equals to 1, the NP-completeness of the problem was established by Harton and Lopez-Ortiz in 2003, and for k greater than or equal to 2, the NP-completeness was shown by Sasaki, Zhao, and Nagomichi in 2008, who studied the distance k vertex cover under the name the beacon placement problem. Our focus lies in the complexity, in the study of the complexity of the distance k vertex cover in classes of graphs that exclude a single graph H as an induced subgraph. When k equals to 0, it was shown in 1982 by Alexeyev that if H has a component that is not a path or a subdivision of the claw, then the problem is NP-complete. And the claw is this little graph of 4 vertices. And on the other hand, the case when every component of H is a path or a subdivision of the claw is widely open. The famous question is whether the vertex cover is polynomial time solvable for PT-free graphs for every integer t greater than or equal to 1, and the result is known for t less than or equal to 6. However, in the case when t is greater than or equal to 7, the problem is still open. But there are quasi-polynomial time algorithms for every fixed t. As said before, we are interested in the complexity of the distance k vertex cover in classes of graphs that exclude a single graph H as an induced subgraph. We will also focus on the cases when k is bigger than or equal to 1. And for those k that are bigger than or equal to 1 and h, we show the dichotomies of the problem. That is, we show that when k equals to 1, the distance one vertex cover is solvable in polynomial time on each free graphs if h is an induced subgraph of P4 plus SP2 and NP-complete otherwise. And when k is bigger than or equal to 2, we show that distance k vertex cover is solvable in polynomial time on h free graphs if h is an induced subgraph of P2k plus 2 plus SPK for some s and NP-complete otherwise. The polynomial time algorithms that we got depend on s and k. However, when h is a connected graph, the time complexity can be improved, and when k equals to 1, it can be improved to linear time on h free graphs when h is an induced subgraph of P4, and when k is bigger than or equal to 2, it can be improved to quadratic time on h free graphs when h is induced subgraph of P2k plus 2. And as before, it is NP-complete otherwise. To show the NP-completeness results, we will first start on the case when h is not a linear forest. That is, when h is not a disjoint union of paths. And we claim that then the problem, that is the distance k vertex cover, is NP-complete. To show NP-completeness, we consider what happens when h contains a cycle and what happens when h contains a claw. When h contains a cycle, we get the lemma that says that subdividing an edge 2k plus 2 times increases the minimum size of a distance k vertex cover by exactly 1. This lemma is a generalization of the statement from Pollack in 1974 in the case when k equals to 0. And this lemma can be used to show that that the distance k vertex cover is NP-complete on h free graphs whenever h contains a cycle. And how to do that? If we have a graph h that contains a cycle c, we can, and a graph arbitrary graph g, we can subdivide every edge sufficiently of g sufficiently many times so that g does not contain the cycle c. And if g does not contain the cycle c as an induced subgraph, then g is c-free, and that implies that g is also h-free. This gives us a reduction from the distance k vertex cover on graphs in general to distance k vertex cover on h free graphs. And since, as seen before, the problem is NP-complete on graphs in general, it is also NP-complete on h free graphs whenever h contains a cycle. Now, when h contains a claw, we show that for every integer k greater than or equal to 1, the distance k vertex cover is NP-complete for line graphs of bipartite graphs and line graphs of planar graphs. And since every line graph is claw-free, this theorem readily implies that the distance k vertex cover is NP-complete on h free graphs whenever h contains a claw as an induced subgraph. Now, this concluded the case when h is not a linear forest. Let us see what happens when h is a linear forest. One might assume that the problem becomes polynomial. However, that is not true in every case. And this theorem will tell us more about it. We show that the distance one vertex cover is NP-complete on P5 and 2 P3 free chordal graphs. And for every k greater than or equal to 2, we show that the distance k vertex cover is NP-complete on 2pk plus 1 free chordal graphs. And how do we do that? If we have a graph G, we can take its vertex set and make out of it a clique, call it Q. And for every edge of G, we take the same edge in Q and append to it a ladder. That is this graph that has k vertices on each side. And for every cycle of length 4 in the graph, we connect the opposing edges, making this cycle complete graph on 4 vertices. If we denote by G prime the newly obtained graph, then for k equals to 1, we can check that G prime is P5 free, as well as 2P3 free. And for k greater than or equal to 2, we can see that G is 2P k plus 1 free. Also, in every case, that is for every k greater than or equal to 1, the obtained graph G prime is also chordal. Now, G prime can be obtained from G in polynomial time, which allows us to have the following reduction from the vertex cover on graphs G to the distance k vertex cover on the graphs G prime. Namely, we claim that G has a vertex cover, call it C, of size at most L, if and only if G prime has a distance k vertex cover D of size at most L. And if we have vertex cover C of G, then we can define D to be the same set C, the copy of the set C, and every edge of G is covered. That is, for every edge, at least one of its endpoints is in C, so therefore it is in D, and therefore every edge of the ladder will be covered by that vertex because the furthest away edge from both endpoints of E is the opposite edge, and that opposite edge is a distance exactly k. So every other edge will be a distance less than or equal to k, and every edge inside Q is a distance at most 1 from that endpoint in E. So every edge will be covered. On the other hand, if we have distance k dominating set D in G prime of size at most L, then we can transform D in polynomial time such that D is a subset of Q. And when D is a subset of Q, we can take C to be a copy of the vertices in D, and any edge in G will have appended to it a ladder in G prime. So since that ladder is covered by a vertex, since that ladder is covered by D, and the only vertex that can cover the opposite edge of E is one of the endpoints of E, we have that at least one of the endpoints is in D, and therefore it is also in C, making C a vertex cover. And this defines as a reduction from the vertex cover on G to the distance k vertex cover on G prime. And since the vertex cover is NP complete on graphs in general, the distance k vertex cover will be NP complete on the newly obtained graphs. And the newly obtained graphs are P5 and 2P3 free chordal graphs for k equals to 1, and for k greater than or equal to 2, the newly obtained graphs are 2pk plus 1 free chordal graphs. Now, why is why is it important that our graph is chordal? In the case when k is equal to 0, that is for the vertex cover, the vertex cover is solvable in polynomial time or chordal graphs. However, we see that when k is bigger than or equal to 1, the distance k vertex cover becomes NP complete on chordal graphs. Now, this concludes the NP completeness results in the case when H is a linear forest. Now we will prove the opposite, that is when H does not contain P5 and 2P3 in the case when k equals to 1, and when H does not contain 2pk plus 1, when k is greater than or equal to 2, we will show that the distance k vertex cover becomes polynomially time solvable. But first, let us define the notion of the dominating set in a graph G to be a subset S of the vertex set such that every vertex not in S has a neighbor in S. In addition, if S induces a connected subgraph, we say that S is a connected dominating set. This allows us to have a look at the following theorem by Canby and Schott from 2016, who stated that if G is a connected PT3 graph for some t greater than or equal to 4, then G contains a connected dominating set S such that the subgraph in G induced by S is either PT minus 2 free or isomorphic to PT minus 2. Also, have a look at the following observation that says that if we have S, if S is a dominating set in G, in a graph G, and S prime is a subset of S that is also a distance k minus 1 vertex cover in the subgraph in G induced by S, then S prime is a distance k vertex cover in G. Those two, that is the theorem and the observation, can be used to prove the following lemma that says that for every integer k greater than or equal to 0, every connected P2k plus 2 free graph G has a distance k vertex cover that induces a path of order at most 2. Now let's see how we can prove this lemma. We will do it by induction on k. If k is equal to 0, then our graph G is P2 free. That is, G is edgeless. On top of it, G is connected. So G is a graph with at most one vertex. And therefore, the statement trivially follows. Suppose now that k is greater than or equal to 1. Then G is P2k plus 2 free. That is, G is PT free for t equals 2k plus 2, which is bigger than or equal to 4 since k is bigger than or equal to 1. So as said before, G is connected and 2pk plus 2 free. That is, G is connected and PT free for t greater than or equal to 4. So we can apply the theorem by Canby and Schott to get that G contains a subset S that is connected dominating set in G, and G of S, the subgraph in G induced by S is either PT minus 2, that is P2k free, or isomorphic to P2k. That is, G of S is isomorphic to P2k. If G of S is P2k free, then we can apply the induction hypothesis and conclude that G of S has a set S prime that is a distance k vertex cover that induces a path of order at that is a distance k minus 1. S prime is a distance k minus 1 vertex cover that induces a path of order at most 2. On the other hand, if G of S is isomorphic to P2k, we can denote by V1 up to V2k the vertices of the of G of S, and take S prime to be the set Vk plus 1. Then we can observe that S prime is a distance k minus 1 vertex cover of G of S, and on top of it, S prime induces a path of order most 2. So in both cases, S prime is a distance k minus 1 vertex cover. So by applying the observation, we conclude that in both cases, S prime is a distance k vertex cover of G. And in both cases, again, S prime induces a path of order at most 2, which proves the lemma. Now, how can this lemma help us? This lemma implies the following theorem that says that for every integer k greater than or equal to 1, there is an algorithm with running time quadratic that takes as input the P2k plus 2 free graph G and computes the minimum distance k vertex cover of G. And the minimum distance k vertex cover of G can be computed by checking every subset of G of size 1 and every subset of G at size 2 that is also connected, and finding the minimum distance k vertex cover with a breadth first search. Note that in the case when k equals to 1, the running time can be improved to linear time because the graph G will be P4 free and therefore of bounded click width, and known results will imply the linear algorithm. This concludes the case when H is connected. Now let us see what happens for H in general. In the case when k equals to 1, we have the following lemma that says that for every integer s greater than or equal to 0, every connected P4 plus SP2 free graph G has a distance 1 vertex cover that induces a linear forest of order at most 2s plus 2. And when k is greater than or equal to 2, we have the lemma that says that every connected P2k plus 2 plus SPK free graph G has a distance k vertex cover that induces a linear forest of order at most Fk of s, where Fk of s is this function. Those two lemmas combined tell us that if G is as defined here, G will have a distance k vertex cover of bounded size. That means the minimum distance k vertex cover will also be of bounded size. So the two lemmas will imply the theorem that says that for every two integers k greater or equal to 1 and s greater or equal to 0, there is a polynomial time algorithm that takes as input P2k plus 2 plus SP maximum from k and 2 free graph G and computes the minimum distance k vertex cover of G. And an algorithm that runs in polynomial time is the following, which takes a graph G and for every connected component of G checks every subset of size, every connected subset of the vertex set of the component of size at most Fk of s or 2s plus 2, and finds a minimum distance k vertex cover of that component. And if you do that for each component, we can take a union of the solutions to get a minimum distance k vertex cover of the whole graph G. This result concludes the dichotomy for the case for general H. And as seen before, we also had similar results, but improved in time for the connected case. Only the difference is the time in the connected case does not depend on k, whereas the case in general, that is the time in general, depends on both s and k. Now, a similar approach can be used to solve other distance variants of domination and covering problems, which will be included in my master thesis. That ends the presentation. Thank you for the attention.